Okay, so I'll post the recording on YouTube afterward. But welcome everyone. I hope you had a good week and are ready to go and do a little bit more trigonometry. Hi, how are you?
How you doing?
Good, Harrison. How's it going?
Thank God.
Okay, good. Okay, so all right, we got another Emmanuel. Yeah, so you can type your name into the chat now, and I'll get I'll have a record of your attendance. Let me just write that. Please type your name into the chat. Okay, so all right, people are all coming on now. Okay, it looks like everybody just got their data 10 minutes later or so. All right. Okay, well, why don't we start off because we are a little bit late. So I do want to start by going over the homework because there were a couple of tricky problems on it. One of them involving these angles of elevation, which we had special requests to do a few examples of. So we'll do two more examples of that today. Let me just mute everybody to get rid of the background noise. Okay, so the first one is a proof, but it's a pretty short proof. So it says, show that if we have an angle between 90 degrees and 0 degrees, that the sine of the angle is the same as the cosine of 90 degrees minus the angle. And so the key to this, of course, is drawing a right triangle, because this is how we do trig functions. We know that they have to do with the right triangle, and we have an angle theta, and maybe we can label the sides of this triangle as A, B, C. Then we have that sine of theta, by definition, this is the opposite side over the hypotenuse, which is equal to A over C. Now the question is here, where does 90 minus theta show up here? So what angle in this triangle is 90 minus theta? Anybody want to, is there an angle in this triangle that measures 90 degrees minus theta? Well, we don't have that many angles to work with, right? I mean, this angle here is 90 degrees. This angle here is theta. And this angle here, maybe I'll call it alpha. And we know from a triangle, we know that 90 degrees plus theta plus alpha has to equal 180 degrees, right? Because the angles add up to 180. So this tells us that theta plus alpha is equal to 90 degrees by subtracting off the 90 from each side. And this tells us also, subtracting off theta from each side, that alpha is equal to 90 degrees minus theta, right? So it turns out this alpha here is actually 90 degrees minus theta. And so now that we have that, well, what is cosine of 90 degrees minus theta? Well, then cosine of 90 degrees minus theta, well, 90 degrees minus theta is cosine of alpha. And what's cosine of alpha? It's the adjacent side over the hypotenuse. And when we take the adjacent side over the hypotenuse for alpha, the adjacent side is A, and the hypotenuse is C. So this also gives us A over C. And what we see is that these two things are equal. So I can say, since sine of theta and cosine of 90 degrees minus theta are both A over C, that means they are equal. Okay, so good. All right, so sine of theta and cosine 90 degrees minus theta are both A over C, and that means that they're equal. Okay, so this works for any angle between 0 and 90 degrees. In fact, it works for any angle at all. We'll talk today about how we do sine and cosine for angles that are not between 0 and 90 degrees. But for now, at the very least, we see that for angles that are between 0 and 90 degrees, that sine of one angle is cosine of the other one. And so, for instance, if we see on our chart over here, right, for 30 degrees, sine of 30 degrees is the same as cosine of 60 degrees. They're both, 1/2. And sine of 60 degrees is the same as cosine of 30 degrees. And sine of 45 degrees is the same as cosine of 45 degrees. And even this, we didn't prove it because we had to assume the angle is between 0 and 90, but sine of 0 is the same as cosine of 90, and cosine of 0 is the same as sine of 90. Okay. So, okay, good. Everybody's coming in. Please remember to type your name into the chat if you haven't done so already, so that we have your record for attendance. Okay. All right. So any questions about this exercise number 1? Yes. Techno K15K. I think if you can. Oh, Emmanuel. Sorry. Yes. Or Techno K15K. I don't know who you are. Also, yeah, if you're Techno Spark or Techno K15K, if you can, to please type your real name into the chat, just so that I know who you are. All right, was there a question? Okay, so we'll go on to the next homework thing. So suppose a right triangle has hypotenuse of length 5 and one angle measuring 37 degrees. What are the lengths of the other sides of the triangle to the nearest tenth? And for this, for all of these problems, the key is drawing a good picture and labeling your picture correctly. If you can draw the right picture and label it correctly, then you can usually solve the problem. It usually just becomes algebra. Okay, this will be especially important for exercise 3. But for us, these first 2 pictures are easy because they just require drawing one right triangle. I'm just going to draw the same right triangle I always draw. So this is my right triangle, and the hypotenuse has length 5, and I have an angle here, which is 37 degrees. Maybe that's not a great drawing because this angle looks like it's more than 37 degrees, but it will be okay for now. So we need to find the lengths of the other side of the triangle. Any variable that you're trying to solve for, it's good to give it a name, so we can call them x and y. And so now what we should have is, in terms of trigonometry, we should have a simple equation for x and a simple equation for y. So what equation do we get for x?
Hello.
Yes, hello, Abraham?
Yes, for the equation for x is
Mm-hmm.
the sum of 37 degrees
Mm-hmm.
is equal to x over 5.
Right. Great. So this gives us that x is 5 times sine of 37 degrees. And this turns out to be, said round to the nearest tenth. This gives us that x is going to end up being about 3.0. This is what we get for 5 times sine of 37 degrees. You need a calculator for that. You can't figure them out. You can't figure that out on your own. You generally need a calculator there. Okay. Okay. Great. Okay, yes, Theophilus, question? Theophilus, you need to unmute yourself. I can't hear your question. If that's what you're doing, raising your hand for a question. All right. No. Okay, I can't hear you, so I'm not going to be able to. I'm not going to be able to answer the question. Okay, so exactly. So you have 2 choices. So here we have x is 3, right? So this x over here is 3. And so we know that the triangle is 3, 4, 5. Like once we have a 3 and a 5, we can figure out the 4. So you could either do that with the Pythagorean theorem, or you could do the same equation, but for y, which is going to be the same thing, except that you have cosine of 37. So this is equation 1, and equation 2 is going to be cosine of 37 equals y over 5. That's going to give you that y equals 5 times cosine of 37 degrees. And if you do this with a calculator, you get that y is roughly 4.0. Okay, so we have 4 over here. So it turns out that this is the 3, 4, 5 right triangle. Up to a pretty close approximation when rounded to the nearest degree, the angles in a 3, 4, 5 right triangle are the right angle, a 37-degree angle, and a 53-degree angle over here. Okay. All right. So this is a pretty standard right triangle trigonometry. Excuse me. We'll get to the hard question next, but before that, any questions on this problem? Okay. No questions? Okay. All right, so let's do the next one, which is the harder question, okay? So 2 observers, so a big trigonometry word problem that uses angle of elevation. So 2 observers spaced 400 feet apart look up at a hot air balloon flying between them. One measures the angle of elevation at 40 degrees and the other measures it at 50 degrees. And then we want to know how high is the balloon flying? Okay, and the hint is to draw the diagram carefully. That's always the hint for every trigonometry problem, is to always just draw the diagram carefully. So let's look piece by piece. So we have 2 observers, say 1 and 2, and they're 400 feet apart. So we'll draw this diagram to start with here. And this is 400. Maybe we could call it observer A and observer B. So then a hot air balloon is flying between them, right? So the hot air balloon is somewhere here. Now note, this doesn't mean it's exactly halfway between them. It just means that it's somewhere between them. So this is the balloon. We could call it C, which is the balloon. Okay. And so 1 measures the angle of elevation at 40 degrees. So I can draw this line over here. We could call that A is going to be 40 degrees. And 1 measures the angle of elevation at 50 degrees. That's B over there. We could call this 50 degrees. And then that's all that it says. So this is all of the information that we have, 400, 40, and 50 degrees. And so we want to know how high is the balloon flying. And the hint says, draw the diagram carefully, and you may want to label the distance on the ground from one observer to the point directly below the balloon. So it seems like this point directly below the balloon is very important because, first of all, we're trying to measure how high the balloon is flying. So if we draw this straight line down so that it's perpendicular with the ground, right? It makes these right angles here. This is H. This is what we want to solve for. But what also might be useful is to label the distance on the ground from one observer to the point directly below the balloon. Let me redraw this line so it's a little straighter. Let me redraw this line so it's a little straighter. Let me draw it straight down like this. This looks a little better. No, that doesn't look better. It's very hard to draw straight lines on this tablet. Okay, so here we are. We have our right angles here. So let's label the distance on the ground from one observer to the point directly below the balloon. So if this is H, I can call this distance here X, right? So X is exactly this distance, right? And if this distance over here is X, how can I label this distance? What's that going to be?
It'll be 400 minus X.
Exactly. So 400 minus X. Thanks, Ed. So this distance here is 400 minus X. Okay. So now I claim we have all the information we need to solve this problem, right? We've got X and H and 40 degrees here, and we've got 400 minus X and H and 50 degrees over here. So what equations can we set up that relate H and X?
Okay, so we can look at maybe probably for the two angles, we can be looking at the opposite and the adjacent side. That is
Mhm.
tangent,
Right.
right?
Yep.
So you can tangent, then we'll have two equations over there. Then at last,
Mhm.
we can equate the two equations. So that is from point A, where we have the 40 degree, we have tangent 40 degree equal to h over x.
Mhm.
And point B, we'll have tangent 60 degree equal to h over 40 minus x.
Right. 400 minus x. Good.
Yes.
Mhm.
Okay. So we can make h our subject. We'll
Right.
make h our subject, then we can put the two equations and
Great.
solve.
So great. So equate expressions for h. Right. So what do we
Yes.
get?
So we have h is equal to x tangent 40,
Mm-hmm.
and h is equal to 40 minus x into parentheses tangent 50.
Great. All right. Excellent.
Okay.
Good. And so now what you see we have here, right, is what we have here is an equation in one variable, right? We have all of these x equations that are in one variable we can solve. So remember, we had this procedure last time. You draw the picture, you write down the trig equations, and then you equate in one variable. You should usually have some side that's part of two different triangles. And so you can equate its two expressions using the triangle. So this is exactly what Ed did. So, and this is now something we can solve. Okay, so if you want to solve this equation, we have that x tangent of 40 is equal to 400 tangent of 50 degrees minus x tangent of 50 degrees. Okay, and that means that we can put the x on the other side. We're going to get x tangent of 40 degrees plus x tangent of 50 degrees equals 400 tangent of 50 degrees. And that gives us that x times tangent of 40 degrees plus tangent of 50 degrees equals 400 tangent of 50 degrees. And I'm running out of space. Well, I'll write the last thing here. So x in this case is going to be 400 times tangent of 50 degrees divided by tangent of 40 degrees plus tangent of 50 degrees. And so actually, did anybody do this problem? Does anybody have what this is in decimals? I mean, I can do it also, but if you have it already, you can just tell me. I'll just do it on the calculator now. So 400 tan 50 degrees divided by tan 40 degrees plus tan 50 degrees. Okay, so this should be 234.7. Okay, so this gives us, I'm going to start a new page. So this gives us that x is about 234.7 feet. So now we just need to remember that this is not, the question that we want to solve is not x. It's good to know what x is, but what we really need to know is h. But the good news is that we now have an equation in terms of x and h and x. So once I know what x is, h is just going to be x times tangent of 40, right? We have this equation already. So h is equal to x times tangent of 40 degrees, which is equal to, which is equal to 234.7 times tangent of 40 degrees, tangent of 40 degrees, which is equal to, let me write this down, 2.7 times tangent of 40 degrees, which is about 196.9. This is what I have. Right. It should be 196.9 feet. Okay. So so this is a So this is the answer. This is how high the balloon is, and it's kind of nice to know that you can tell that only by knowing how far apart you are and what your angle of elevation is. And we could have also used this equation for h. If I plugged in x equals 234.7 feet here, did 400 minus that times tangent of 50, we should get the same answer for h. So this is a good check. So check that 400 minus x times tangent of 50 degrees gives the same answer with x equals 234.7. Okay. So it's worth, you can try that in your calculator, but the point is it should give the same answer because we're solving for both of these equations together. So h is simultaneously given by this expression, x tangent of 40, and also 400 minus x times tangent of 50. So once you've solved for x, the point is that both of those equations should be the same. So they should give you the same h. Okay, so these problems are not so bad once you've drawn the correct diagram. And generally, when you draw the correct diagram, you're going to have two triangles. And for each of those triangles, you're going to get an equation involving the two unknown quantities. Okay, and once you have those two equations in two variables, then you can solve, and everything's going to be okay. Okay, so we're going to do one more example today that involves an angle of depression. But before we do that, any questions on this problem? So this is exactly right. Okay. Okay, great. All right, so let's go on to what we're going to talk about today. This is just the review of the special values. We don't need this right now. So let me just recall this angle of elevation again. So remember, we have this percentage grade that we did a couple of examples about last time. We're not really going to talk about it today, but it's here on the slide that the percentage grade, let me just redraw this picture that we have. So the percentage grade, if this is theta, this is the angle of elevation. This is a right triangle, and this here, and if I have y and x, then y over x equals the percentage grade, which we write as a percent. So what I do want to say that's new here is this angle of depression, which is the same thing as an angle of elevation, but it's from the perspective of somebody looking down at something instead of from the perspective of somebody looking up at something. So this is the angle of elevation, is when you're standing at a bottom of a road and you're looking up. The angle of elevation would be something like this. You have like somebody standing here, right? Somebody standing at the edge of a building or on a cliff or something like that. And you have a vantage point over here. Okay, and this person is looking down, 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 down there to this point. And so what's the angle of depression? Well, we draw an imaginary horizontal line out from where the person is standing. And then over here, this is this angle theta. And this angle theta here is the angle of depression. And one thing that's true is that the angle of depression from the perspective of the person standing on top is the same as the angle of elevation from the perspective of the person or the object at the bottom, right? Because if I draw this horizontal line also, these are what are called alternate interior angles, which means that they're going to be equal to each other. So this is the same angle theta over here, and it could be viewed as an angle of elevation from whoever's down here at the bottom. Okay, so the angle of depression is the same thing as an angle of elevation. It's just from the perspective of the person at the top rather than the perspective of the person at the bottom. Okay. Okay. So okay, good. So let's do an example with this. All right, so angle of depression, another word problem. So a 6-foot tall man, or actually let's say we're a little bit taller than him so that his eyes are 6 feet off the ground, so maybe 6 feet and a few inches, stands at the edge of a roof of a building and sees a small patch of grass at an angle of depression of 30 degrees. An ant standing at the man's foot sees the same patch of grass, but at an angle of depression of 25 degrees. And the question is, how tall is the building and how far away is the patch of grass? Okay, so with all of these problems, the first thing you have to do is draw a diagram. Okay, so let's draw our building here. Put some windows in if we want. All right, so here is our man. Okay, and here's the little ant right there. Okay, and here's our patch of grass all the way over here. Right, and so what do we have? Well, we have an angle of depression from the man when he's seeing something at an angle of depression. Usually we've been ignoring how tall the observers are, but for this question it matters. So he's seeing something, he's 6 feet tall, so his eyes are 6 feet above the building, right? So if this person is drawing an angle of depression, let's draw it like this. Oh no, sorry. I'm going to draw from his eyes down to here. Okay, this is going to be at an angle of depression of 30 degrees. Put that out here. So this angle here is going to be 30 degrees. Okay. Oh, I should sorry, I should have, yeah, okay, this is fine, 30 degrees. Now an ant is the same place here, but is 6 feet lower. This ant sees the grass. I'm going to draw this right here. And this ant has his own angle of depression, which here is going to be 25 degrees. Okay? And the other thing that we know is that the man's eyes are 6 feet above the ant's eyes. So we'll call that 6. Okay, and so the question is, how tall is the building and how far away is the patch of grass? All right, so the question is a little bit tricky, but in the end, it's not going to be any harder to solve than these other ones that we've been looking at, right? The only issue is how to set it up correctly. So, right, we have this diagram. Now, the question is asking two things. How tall is the building? Let's call that H. And how far away is the patch of grass? Well, if it's asking us to measure a distance, we should probably draw that line, right? So let's draw this line over here to the patch of grass. This is going to be X, right? So what we want to know is how far away, we want to be able to solve for H and X. So what I'm going to do is I'm going to try to write the equations on this page, and then we'll solve them on the next page. And for here, we might want to use these alternate interior angles, right? So this is 25 degrees here. That means that this angle over here is also 25 degrees. And if this is 30 degrees over here, that means that this angle here is also 30 degrees. Right, I'll draw it in green so that you know it goes the whole way. Okay, and so now with this, I claim that we have enough information to solve the problem. So what equations can we set up? Say for X. Anybody want to give me a trigonometric equation we can write that relates H and X?
Oh, we can start with,
Sergeant,
hello?
Sorry?
hello.
Yeah, Emmanuel, is the question?
Yeah, I'm looking at tangent.
Yeah. Sorry.
And you
Hello?
are asking for the trigonometric function used
Yeah.
in this situation.
Yeah, yeah, well, tangent, yes. But I want the full equation. So how can we set
Okay,
up the
yes,
full
sir.
equation involving tangent? So yeah, I think
And-
Ed was answering, yeah.
Okay, since we have the height of this main here to be 6, that it is 6 feet.
6 feet, yeah.
Okay, so then we're going to use the first one, the tangent 30 degree.
Yeah, I'm seeing tangent.
Right. So
Yes,
exactly,
Are you there?
we're
Emmanuel.
going to use it.
Yes, I'm hearing you.
Yeah.
I'm getting you. Yeah,
So we're
Emmanuel.
going to
Yeah,
use the tangent
tangent.
30 degree and
Right.
the opposite or adjacent.
Right.
Then we'll be able to find the x.
Right. And so what do we have for opposite and for
So-
adjacent here?
So we have the tangent 30 degree opposite will be the 6, and the
Be
adjacent
careful.
will be the x.
Okay, so the adjacent is the x. I agree with you. Let's be careful. What is the opposite side here?
Yeah, that the opposite side will be h plus 6.
Exactly, right? H plus 6, right? Because we're
Okay.
looking at this triangle over here. It's this whole triangle with the 30 degrees. And so this side is x, and this is the full thing. So this is going to be h plus 6.
H plus x. Yes, that's correct.
H plus 6, right? Great. So that's the first equation. We have the tangent of 30 degrees equals h plus 6 over x. And what's the other equation that we get?
That's
Tangent
the
of
second
25 degree.
Yeah.
Tangent of
tangent of
25.
Yep. Equals, let's say again, opposite over adjacent. And that's going to give us what?
H or x.
Great. Okay, so this is the key. Once you've done this, solving the rest of the problem is not hard. The work is drawing the diagram correctly and then setting up the correct, knowing the correct trigonometry function you're going to use, because eventually, what do we have in both of these equations? We have x, right? So we're going to be able to isolate x, and then we'll be able to solve for h by isolating x. Okay? So I'll go and I'll solve the equation, but before I do that, are there any questions about how we got these two equations? Because this is most of the work. Once you have the two equations, you can just go with it and do some algebra. So I want to pause for questions before I solve the equations. Okay, so let's just solve this. I'll rewrite the equations here. So we have tangent of 30 degrees equals h plus 6 over x, and tangent of 25 degrees equals h over x. So I'll just go through this quickly because this isn't really the interesting trigonometry. So we have that x is equal to h plus 6 over tangent of 30 degrees, and x is equal to h over tangent of 25 degrees. So this gives us, so now we can equate them to each other. So this gives us that h plus 6 over tangent of 30 degrees equals h over tangent of 25 degrees. And now we can cross multiply, and we get the tangent of 25 degrees times h plus 6 equals tangent of 30 degrees times h, which is the same thing as h times tangent of 25 degrees plus 6 tangent of 25 degrees equals tangent of 30 degrees plus times h. And this gives us 6 times tangent of 25 degrees equals h times tangent of 30 degrees minus tangent of 25 degrees. And this gives us that 6 tangent of 25 degrees divided by tangent 30 degrees minus tangent 25 degrees equals h. And so let me just do that on the calculator so that you don't have to. So we have so 6 tangent 25 degrees divided by tangent 30 degrees minus tangent 25 degrees Okay, so this gives us 25. This gives us that h is roughly 25.2 feet. So that's the building. And then now we can solve for x. And then we have x is equal to h over tangent of 25 degrees from this equation over here. And so h over tangent of 25 degrees, we have 25.2 divided by tangent of 25 degrees. Tangent of 25 degrees, that is 54. Okay, so this is roughly 54 feet. Okay, so this is the answer over here. But again, this part over here I did fast because this is not really the interesting part. We know how to do this now, right? We know how to once we have two equations, we can isolate x and set the other two things equal to each other, and then it's just a linear algebra equation. And once you solve for one variable, you can solve for the other variable. The key is getting these two equations in the first place. And for that, you need to know this diagram. Okay, so just by knowing the difference in the angles of elevation or the angles of depression from somebody right at the building to somebody standing above the building, that's enough to tell you not only how far away is the thing, but also what is the height of the building. So that's kind of cool that you can measure a height of a building by standing on top of it and using a protractor. You could do one with your height and you could do one lying down, and that's enough to measure the height of the building. So that I think is pretty neat. And yeah, and one calculator hint, which is make sure that when you use a calculator that the calculator is programmed in degrees. Often calculators will default to radians if you don't specify degrees. And if you use radians, you're going to get a completely wrong answer here. Okay, so any questions about any part of this diagram, either the trigonometry setup or the algebra? Okay. All right, so if that's good, let's just go on to, so that should be enough for angle of depression, angle of elevation. If people want more problems, I can try to send some over the chat. But by now, I think we see the idea, which is you're always drawing a diagram. There's always going to be two different triangles in the diagram. Now, and those two triangles will always share a common side. So in this case, we have these two triangles. In the earlier case, we have these two triangles, 1 and 2. But there's always going to be two triangles. They're always going to have a side in common. And you can use trigonometry to equate two expressions for that side. And once you have that, you're able to solve for one variable, and then you're able to solve for the other variable. Okay, so that's how all of these work. It might be the two observers are standing on the same side of something, or they might be standing on a different side of something, or they might be on top of each other the way they are in this problem. But the standard idea is always going to be the same. Okay, there's going to be two different observers. They're going to have different measurements, and you're going to be able to compare the two triangles that they make. Okay, so all right, so let's talk a little bit about, for the rest of the day, about how we extend the domain of the trigonometric functions. So right now, every trig function that we're using always has an angle between 0 and 90 degrees because we're defining them using right triangles. And the angles in a right triangle are always between 0 and 90 degrees, right? There's no way around that. So always between 0 and 90 degrees, okay? So what we want to do, though, is be able to define sine and cosine and tangent and all of the other stuff. We want to be able to define them for any angle at all, even an angle that's maybe an obtuse angle, or maybe an angle of 0 degrees or 270 degrees or whatever. And in general, we're even going to define them for every real number. It doesn't even need to be an actual angle. So it doesn't need to be between 0 and 360 degrees. So one of the things that we remember from the trigonometric functions, at least for angles between 0 and 90 degrees, so for acute angles, we've defined tangent is opposite over adjacent, and that's the same thing as, you could view that as opposite over hypotenuse divided by adjacent over hypotenuse, right? These are the same fraction. And well, another way of seeing that is that opposite over hypotenuse is sine and adjacent over hypotenuse is cosine. So this tells us that for angles between 0 and 90, that tangent is sine over cosine, okay? You can do something similar here, and you get that cotangent is cosine over sine. Okay. And then we also have secant and cosecant. We haven't talked about them as much, but the definitions here is that secant is the hypotenuse over the adjacent side, and that's the reciprocal of the cosine. Remember, the cosine is adjacent over hypotenuse. So this gives us that secant is 1 divided by cosine. And similarly, cosecant, which is the hypotenuse over the opposite side, that's 1 over sine. Okay, so if we want to define these trigonometric functions for any angle theta, it's good enough to find out a way to define sine and cosine. Once you have sine and cosine, you get everything else, right? Tangent is just sine over cosine, cotangent is cosine over sine, secant is 1 over cosine, and cosecant is 1 over sine. So once you know sine and cosine, you can figure out everything else, okay? And so we have to figure out how to define sine and cosine. And the way that we do that is by using something called the unit circle. Okay, so our goal for the rest of the day is to define sine and cosine for any angle. And once we know that, then we can define tangent, cotangent, secant, and cosecant just by doing the correct divisions. All right. Any questions here? Okay. All right, great. So, good. All right, so let's go on to the next slide. Okay, so what is the unit circle? Well, the unit circle is the circle in the XY plane that has center at the origin and radius equal to 1, right? So we talked about these circles a little bit when we talked about completing the square last time, but this is a very simple circle, and it just has equation x squared plus y squared equals 1. So this is the x-axis, this is the y-axis, and you have your circle here with the center at the origin, and the radius is 1. And so in general, we measure angles in a counterclockwise direction from the positive x-axis. There's no reason to do this. It's just what people do. And it's good that everybody agrees on one way to do it. Okay, there's nothing fundamental to mathematics that requires this. It's just a convention. Okay, and so if theta is an angle, we define cosine theta to be the x-coordinate where a ray from the origin and angle theta hits the unit circle. And likewise, we define sine of theta to be the y-coordinate where this happens. So maybe instead of drawing it on this diagram, let me give you a bigger picture over here. So this is the unit circle drawn again. This is our x-axis. I'll just extend it a little bit. And so if we have some angle theta here on the unit circle, and remember, theta is measured counterclockwise from the positive x-axis. So this angle is the theta right here. Well, we can look at this point where the ray at angle theta hits the unit circle. I mean, I can extend it onto infinity if I want to, but all that matters is the point where it hits it. This is the point x comma y, right? And so what this tells us is that we have here an x-coordinate of x and a y-coordinate of y. And let's observe from right triangle trigonometry, if we have the cosine of theta is the adjacent over the hypotenuse, well, this is equal to x over 1, which is x. And likewise, sine of theta is equal to the opposite over the hypotenuse, and this is equal to y over 1, and this is equal to y. Okay, so using our normal right triangle trig, if I draw this triangle, the cosine is x and the sine is y. So what the unit circle does is it does something that's pretty standard in mathematics, which is that you have something defined for some small set, for only the acute angles. You find another way of expressing that definition that works in much more generality. So with right triangles, the only angles you can put in are acute angles. But with the unit circle, you could put in any angle. If I wanted to do sine or cosine of 135 degrees, I would just draw this line over here. This has an angle with the x-axis of 135 degrees. And then whatever this point is, the x-coordinate is going to be cosine of 135 degrees, and the y-coordinate is going to be sine of 135 degrees. Okay. Right? So that's it. Okay. So this is what we've got, right? So now using the unit circle, we can define sine and cosine of any angle. You just draw that angle clockwise from the positive x-axis. You draw a ray at the appropriate angle, and you look to see where it hits the unit circle. And the x-coordinate, whatever that is the cosine of the angle. And the y-coordinate, whatever that is the sine of the angle. And we see that this agrees with our standard definitions for acute angles. Here, the x-coordinate is exactly adjacent over hypotenuse, and the y-coordinate is exactly the opposite over the hypotenuse. All right, so, and if we want to see this in general, this is a unit circle with all of the special angles labeled. Okay, so this is a picture with all of the angles that we know. So we know if we draw 30 degrees, for instance, these measures in terms of pi are radian measure. We'll talk about that more next week. But for now, just focus on the degrees. So this is 30 degrees. And what we see is that the x-coordinate is square root of 3 over 2. That's the sine. Sorry, that's the cosine. And the y-coordinate is 1/2. That's the sine. But for instance, if we had 150 degrees, that's kind of the same line as this one. It's just reflected over the y-axis. So the y values will be the same, but the x values will be different. So here, the x value is root 3 over 2. For 150 degrees, it's going to be minus root 3 over 2. The y values here are just 1/2 and 1/2. So over here, we get, for instance here, that cosine of 150 degrees equals minus root 3 over 2, because the x-coordinate, and sine of 150 degrees equals 1/2, because that's the y-coordinate here. Okay, so any questions on this basic kind of application of the unit circle, how it works to define trig functions for every angle? Okay, all right, so that's our unit circle. So I want to say something about reference angles. So for any acute angle theta, if we look at the angles theta, 180 degrees minus theta, 180 degrees plus theta, and 360 degrees minus theta, it turns out these all give the same values of the trigonometric functions up to a plus or minus sign. And I'm going to go back to the unit circle and show you why that's the case. But for example, if we have theta is 60 degrees, what we'll see is that cosine of 60, that's theta, cosine of 120, that's 180 minus theta, cosine of 240, that's 180 plus theta, and cosine of 300 are all the same up to a plus or minus sign. And in that case, what we call this angle 60 degrees, we call it the reference angle for 120 degrees, 240 degrees, and 300 degrees. So let me show you what this looks like on this circle. So I'll use red. So 60 degrees is this point here. What is 180 minus 60? Well, it turns out that that gives you exactly the same angle, but reflected over the y-axis, right? And that's because here we have 180, here we have 180, and here we have 0. And as we move this up to 30, this goes up to 150 if we're trying to do the mirror image. And the angles still add up to 180. And again, we have 45 and 135. The angles still add up to 180, and here's 60 and 120. So if I take two angles that add up to 180, supplementary angles, what happens is that they end up being each other's reflections over the y-axis. And that means the point where the angle, the ray at 60 degrees versus the ray at 120 degrees, where it hits the unit circle, well, if it's a reflection over the y-axis, the y values will be the same and the x values will be different. Likewise, for 60 degrees, 180 plus 60 is 240. What happens when we do 180 plus 60? That's just the same as adding a straight angle, adding 180 to 60. So if we draw the line at 60 degrees, if we do the line in the opposite direction, that's the line at 240 degrees. And so we see that these points are just opposite each other. So if this is 1/2 and √3/2, then this point over here is -1/2 and -√3/2. Okay, so again, the same values, but just maybe with some extra minus signs. And lastly, we have 300 degrees. And this 300 degrees is 360 minus 60 versus here where you have 0 plus 60. And what we see is doing 360 minus 60 is the same thing as going down this way, the same distance as what happens when you go up to 60 this way. And so these angles are actually reflections of each other over the x-axis. And again, we have 1/2 and -√3/2. So for all four of these angles, the sine and cosine are 1/2 and √3/2, but maybe with some extra minuses thrown in. So here we have the red dots correspond to 60 degrees and 180 minus 60 degrees, which is 120 degrees, 180 plus 60 degrees, which is 240 degrees, and then 360 minus 60 degrees, which is 300 degrees. Okay, so these are the red dots, and all cosines are plus or minus 1/2, and all sines are plus or minus square root of 3/2. Okay. And so just back to the slide, the last thing we'll say today, how do we know whether the values are negative or positive? Well, we use what's called the ASTC method. So what you do is you label every quadrant going counterclockwise as ASTC. ASTC, sorry. And you can come up with your favorite mnemonic. The one I learned was all students take calculus. If you have something that you like better, you can use that to remember. But that's how I know ASTC. And what do they stand for? Well, the A here stands for all, the S stands for sine, the T stands for tangent, and the C stands for cosine. And what this tells you is if the angle is in one of these quadrants, which trig functions have positive values? So here, this means all have positive values. This means the sine has positive values. This means the tangent has positive values, and this means the cosine has positive values. So for an example, if we're looking at, cosine of 300 degrees, well, first, find the reference angle. Well, in this case, we have 300 equals 360 minus theta. So theta equals 60 degrees is going to be the reference angle, right? So 60 degrees is the reference angle. The reference angle is always an acute angle. It's always between 0 and 90. So find that reference angle. Number two, evaluate cosine of 60 degrees. This we remember from our table. This turns out to be 1/2. And then three, we use ASTC to see if there is a minus sign. And in this case, well, 300 degrees is in the fourth quadrant, right? I mean, here we have 0 degrees, 90 degrees, 180 degrees, and 270 degrees. So 300 is somewhere here. That's the C quadrant. So cosine is positive. So that means there's no minus sign. So in our case, the answer is no. So we end up getting that cosine of 300 degrees is equal to 1/2. We get cosine 90 degrees, 300 degrees is 1/2. Why? We check the reference angle at 60. We evaluate cosine 60 is 1/2. And then we check the quadrant to see if we need to throw on a negative sign. So in this case, we don't, because we're in the cosine quadrant. And if we look back at the picture, right, well, we see in this quadrant, the x coordinates are positive. That's why cosine is positive, right? And we have our cosine here as 1/2. In this quadrant, the y coordinate is positive. That's why the signs are positive. In this quadrant, the x and the y are positive. That's why cosine and sine are positive. And in this quadrant, the x and the y are both negative. That means sine and cosine are both negative. But remember that tangent is sine over cosine. And so that means that tangent is positive because sine and cosine are both negative. So when you divide them, you get something positive. So we see what's positive, sine here for the y coordinate, tangent here, because x and y are both negative, and cosine here for the x coordinate. All right. Any questions about this, about how we do these evaluations for large angles like 300 degrees? Okay. All right. So if there's no questions, that's basically it for today. So we have, so the first homework exercise is straightforward, just to calculate tangent of 300 degrees using a reference angle, from the chart on page 5. Remember, page 5 is just page 5 is just this chart over here, right? So you can use this if you want to. The second exercise says, suppose A is sine of 40 degrees and B is cosine of 40 degrees. So then can you calculate cotangent of 220 degrees in terms of A and B? So you're doing this in terms of A and B. So this is a no calculator question. And then the third question is a little bit more interesting. So again, A is sine of 40 degrees and B is cosine of 40 degrees. I want you to calculate cotangent of 230 in terms of just A and B. I claim you can do this, that this is not impossible to do, and you don't need a calculator. And then the question is, can you find an expression for it that uses only A, that doesn't use B at all? Okay, so 1 and 2 are pretty straightforward. 3 is a little bit more challenging, although it's certainly doable, and we'll go over it next time. So this is the homework, and as always, I'll send out the notes on WhatsApp so that you can see it, and I'll post the video on YouTube. And then, yeah, so thank you for your attention. And so next session is next week, which is March 1st, and we'll talk about radians, and we'll talk about trigonometric identities. We're going to have 2 classes on trigonometric identities. Next week is kind of the basic trigonometry identities, and then the one after that will be the more advanced trigonometry identities. Okay, so we'll start with basic ones, and then we'll go to more advanced ones. Okay, so thank you again, as always. Please remember to type your name into the chat if you haven't done it yet, so that we have your record for attendance, and we're able to give you data that you deserve. Okay? All right, and thank you very much for your attention. Happy to take any questions. Okay. All right, you're welcome, everybody. We'll do one minute. I'll leave the chat open if you haven't written your name yet, and after that, I'll stop the recording, and we're gonna lose the end. And at that point, you won't be able to type your name anymore. All right, you're welcome, Joyce. You're welcome, Prince. Abraham. Okay. All right, everybody, you are welcome. I'm gonna stop the recording.